Alright, so today we're going to be talking about VSEPR. I've already pre-written the definitions in to kind of save some time. Alright, so VSEPR stands for valence shell electron pair repulsion, and it is a theory. VSEPR is a simple technique for predicting shape and geometry of molecules. And these are some common shapes that you'll find in 3 dimensions for molecules. Now, atomic centers. With VSEPR determined geometry can be joined into larger molecules. Something like glucose, which is a 6-carbon sugar. So I'll draw out like a little rough sketch of that. Okay, let me finish drawing this. Alright. Now, if you take a look at each of these centers, this one it's always kind of abbreviated, but like for instance, if we look at these, we can see that this one goes this way, this one goes this way. It's always going to be a tetrahedral shape for a carbon with 4 single bonds. And no matter how many links it has, the geometry is always going to be determined by VSEPR due to the repulsion of the electrons in each individual atom. It's going to have I know this isn't the best drawing, but about 109.5 degrees angle difference. Now, there are 6 steps, and we're going to be using for our example CH4 and NH3. So I'm going to be referring to those as methane and ammonia from here on out, because that's what they are called. Now, I'm going to go to the next page. The first thing is determine the number of valence electrons depending on the group number in the central atom, or of the central atom. That's electron. Oops. Alright, so this is done simply by looking at the group number. I taught you this when we went over the periodic table, but I'll go over it again real quick. Group 2, 2 valence electrons, and this is a horrible representation. That's not what they're actually going to look like. It's just so you can see it. Group 3, 3 valence electrons, 4, 5, 6, 7, so on. So first step is just determine the valence electrons in the central atom. You're kind of going to be doing the same thing for your attachments, but anyways. Find the valence electrons each additional atom has to bond with. So what this means is we have our C. This is our central atom. Do the first two steps right here. We have our N. So you have 1, 2, 3, 4, and 5. So right now we're looking at 1, 2, 3, 1, 2, 3, 4. And I'm not talking about ionic compounds right now. I'm literally just talking about the two that I mentioned earlier. So we have H, 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 and H. So if we drew lines from each of these, you'd be able to see that, oh, I have 4 available bonds, and the H is determined by group 1 only having 1 valence electron. Same thing over here, we do H, H, and H. So what that means is you can kind of, similar to when we did the Louis dot structure, you're able to piece together how many valence electrons your attachments have and your central atom to kind of figure out what the molecule is going to look like. So that's the third step. I kind of mashed all 3 of them together, and then let's just construct a valid Louis dot structure. Make sure, this is important, show all bonds and lone pairs. So when I refer to lone pairs, I'm referring to if you have a pair of electrons that aren't bonded to anything. That is a lone pair. And that is important for determining the geometry. Now, and another thing to be aware of is elements in period 3 or higher may have expanded octets. May have expanded octets. Okay, so what that means is, I'm going to show you an example. So say I had H2SO4. So right now, this is our central atom. I'm not going to go through the steps of drawing it or constructing it. I already know what it looks like, so I'm just trying to speed this up to show you. Alright, even though this is only going to have 4 attachments, it still has more than, your 8 electrons surrounding the sulfur. You have 2, 4, 6, 8, 10, 12. But I like choosing this molecule because while it does have more, if you look at the chart that you should have with you on Canvas, 1, 2, 3, 4, you have 4 attachments around the central atom and no lone pairs, which would make this tetrahedral for both its electron geometry and molecular geometry. Whereas, say we look at water, water's got 2 bonds and 2 non-bonded pairs. So these lone pairs factor into the electron geometry, giving it a tetrahedral configuration for its electrons with the bonds and the lone pairs. But our molecular geometry really doesn't take these into account except for determining what the electron geometry is going to be so you can figure out the molecular geometry. So our molecular geometry is only going to take into account the bonds. So we would go 4, 2 bonding, 2 non-bonding, because you have 4 total, and that would give you a bent shape, which is why it's drawn like this. Alright, so that's just one quick little example. Alright, so the next step is determine your coordination number there's multiple ways to do this, really. Coordination number is a number of electron pairs. Or you could just, honestly, you could go by the number of attachments. You have 4 right here, it's going to be tetrahedral. 4 right here, tetrahedral. 4 right here, but this one's non-bonding. Even though you have 4 attachments, its coordination number is 4, so it's going to put you in the tetrahedral electron geometry, but this is actually a trigonal pyramidal. Anyway, so on to the next step, because I'm trying to keep this kind of short. So kind of piggybacking on the last thing, the electron geometry is determined by the coordination number and repulsion of electrons, or electron pairs. And what that would kind of look like is balloons. Like if you blew a bunch of balloons up and then, for whatever reason held them in the center, these are the types of geometric shapes they're going to make. So if you look here, it's going to be straight, trigonal, planar, and this would be your tetrahedral, this one is octahedral, and honestly, there's trigonal, bipyramidal. Anyways, the last one is, I'm not really going to hold you accountable for this on the test, but it's just nice to know. Small adjustments are made for lone pairs. So what that means is they're taken into account when determining coordination number, but not the geometry. And they act as a bigger balloon, which will distort the bond angle, making them actually a little smaller. So I'm going to just make sure that you know that distorts bond angles. Making them smaller. Okay, so let's get the picture. Alright, so here would be methane and ammonia. See how this one lone pair exerts a little bit more push on here than this bond does. So it actually distorts the angle just slightly. Water's a little more extreme. I'll put that one in there too. So here's water, right here. And then water has 2 lone pairs, right there and right there. And that will actually distort the angle just a little bit more. So it's not off by a ton, but it is off by 5 degrees. And that's pretty much all you guys need to know for VSEPR. I would suggest that you get comfortable reading the chart that I posted on Canvas. And recognizing patterns helps a lot. If you want to just play with making the molecules that were on your homework, you can go here, which has also been in the course link since the beginning of the year. but you haven't had a reason to use it. But you can go there and make the molecules and see the different shapes. And that's pretty much it.